Hi, everyone, and welcome to another video of Chem with Com. Today, we are going to do, this is a part of a two-part series. This is Intermolecular Forces, States of Matter, and Energy. All right, this is a very conceptual couple chapters, so not a lot of math. So let's tackle this. All right, specifically, this one's going to be called intermolecular forces. Let's analyze that word real quick. Inter means like within two different, like interstate means going between two states. Internet means going, between two computers or many computers. So inters between, two different things. These are forces that occur between molecules. So we have different molecules. Remember, molecules are more than one atom, and there's some sort of force occurring between those. We're trying to figure out what that means, right? So we're going to start there. All right. So this is conceptually, this is a direct continuation from topic 4. Topic 5 was nomenclature. We had to learn how to name things. And then chapter 6, topic 6 was like learning how to do math and stuff. And then we're going back to this to jump into this. All right. So materials experiencing physical changes will have different physical properties. So physical changes are something like taking solid water, which we know as ice, changing it to liquid water, which we know as water, and then gaseous water, which we know as steam, right? But they all are going to be just water. So we're just changing the physical states of these. We're not changing the chemical makeup. As you increase temperature, you can make solid water into liquid water. Keep going with a higher temperature, it becomes vapor water, which is now vapor water, which is steam, right? Now, but what's holding these things together, right? Gas, there's no forces between, or no um, forces are not currently occurring in between those molecules, right? Are those particles because they are far apart. Far apart, no forces. Here we're starting to see these forces possible. So closer, so some forces. Here we have, they're pretty much packed together, right? Packed together. So yes, forces, yes, right? And the strength of these, or they're just more intermolecular forces here because those things are packed tighter together. Here, when they're liquid, they're kind of moving around a bit. And what's happening is that those forces are forming and breaking, forming and breaking. Whereas these gas particles on the far right, those forces only occur when those particles touch, right? Which is it happens, but not as frequent as liquid, or definitely not as frequent as a solid, right? So again, these are just physical changes because it stays the same formula, but we're going to start dealing with these things called intermolecular forces. So intermolecular forces govern these physical states, right? You cannot have a solid without these particles interacting with each other, right? Those interactions, or those intermolecular forces, keep those particles together. Without particles being held together, they're all going to be gas, right? They're not even going to be liquid, because liquid, some of the intermolecular forces, what happens is for liquid, sometimes they're, being attracted there, but that it'll turn and be attracted to something else. And then this one will turn and be attracted to something else, right? So they're mobile. Forces are forming and breaking, forming and breaking. These solids, they're fixed in place, they're holding each other together. But again, if there's no intermolecular forces, there's nothing to keep that thing together. It's like building in furniture from IKEA, right? You need the screws and bolts to hold things together, or else the whole thing falls apart. Same with these solids and liquids, right? So again, intermolecular forces govern different physical states. These intermolecular forces are weaker than the bonds that we learned about, right? They're weaker than covalent or ionic bonds. So this is a covalent bond. Covalent bond. We also have ionic bonds, something like this, where you have like sodium. Let me write it a little better. Sodium 1 plus, and it has chlorine with all its electrons, 1 minus. These are much stronger than an intermolecular force. Intermolecular force, right? Covalent bonds, these are all kind of strong. These are very weak, right? That's why when you boil water, you're not breaking apart water, but you're separating individual water particles, right? So if we look at, remember hydrogen bonding, we can do this. And I think we talked about hydrogen, or sorry, we talked about polarity. So this is polarity, right? We have that partially negative side, partially positive side, partially negative side, partially positive side. But these hydrogen bond, when you boil water, right, these break first because they are weaker, right? These hydrogen oxygen covalent bonds, those don't break if you boil water, right? All right, so let's continue. Again, this is a very conceptual chapter, not a lot of math, but you still have to learn this stuff. This is really important stuff, right? So the three intermolecular forces we're going to talk about, and we'll get into the details, are the weakest are called dispersion forces. These are temporary dipoles, and we'll revisit this word temporary dipoles. We'll visit these individually. Dipole attractions are the second one. So let's just number these 2 and 3. And the strongest are going to be the hydrogen bonds. We'll go in order. We'll try to explain these and we'll get you through these intermolecular forces. Okay, so this is one that we should be familiar with, and we're familiar with this because of the polarity chapter. I believe that was topic 4, again, a continuation from that. They occur between two or more polar molecules. So what's a polar molecule? Well, it's a molecule. Again, let's use water. Let's use something different. Let's use HCl, right? There's shared electrons between the H and Cl. What happens is the Cl is more what's called electronegative. So this side is slightly more negative. This side is slightly more positive, right? And we learned that if you could split this molecule in half, or if you could split this molecule and there's a partially positive side and a partially negative side, this is polar. Because it's polar, these molecules can stick together. What happens if there's another HCl, right? What happens here is that this is still partially negative. This side's partially positive. So these will interact. Let me just draw a different color to, right? Those are going to interact. And if there's another one there, let's get a red pen. HCl, right? It can chain and it can do different things, and it could be this long, complicated mass of molecules. But this can happen between other molecules as well. So let's say we have something like CH2O. So CH2O would be on that side. So C, H, double bond to O, right? This is going to be the partially negative side. This is the partially positive side. So that will interact. It could also interact with stuff like water. Water is also polar. A single bond to O, right? This is partially negative. This is partially positive. That can interact. So the requirement for a dipole-dipole interaction or a dipole-dipole attraction is you have to have at least two polar molecules. Because again, you have a dipole for one and you have to have a dipole on the other, which means two polar molecules because you need a negative side and a positive side to attract the either negative side or the positive side or the other. So it occurs between two or more polar molecules. You can have a whole jar full of like billions and billions and billions and billions of different molecules, all different, right? But some of those are different and they can all mix together well because those are all chaining from the positive side to negative side to positive side. All right. This is just a pretty much a direct review from topic 4. So this is where we're going to start. We're going to move on to some of the new stuff, right? So again, dipole-dipole interactions are between two polar molecules, two or more polar. You can't have a dipole-dipole interaction or attraction with one single molecule. Just like you can't do a handshake by yourself, right? You need someone else to interact with you to do that handshake, right? So, all right. Let's move on now to hydrogen bonds. Now, this is just the strongest form or strongest, I guess, form of polarity. So strongest form of polarity, right? Something can hydrogen bond if a hydrogen is directly covalently bonded to a nitrogen, oxygen, or fluorine. And if you look on the periodic table, those electronegativities are way up here, right? So they're the three most electronegative atoms on the periodic table. The idea is those are so electronegative, it's pulling the electrons very, very, very close to nitrogen, which makes this side much or a little more negative, right? It's still partial negative, but it's strong. It's stronger than a normal polarity. Same with oxygen. It holds those electrons really far away from hydrogen. So this side is kind of a little more negative than a normal kind of polar bond. And then HF, F is really negative. Fluorine's very, very electronegative. So it's going to be hovering way closer to the fluorine than it is the hydrogen. So it's going to be slightly more polar than or stronger than the other polar molecules. And again, it's the hydrogen directly connected to a nitrogen, hydrogen directly connected to oxygen, hydrogen directly connected to a fluorine. So now if you look at something like this, HCO, right? Not hydrogen bond because H not directly connected to oxygen. All right. If it's directly connected, we're all good. Perfect. Hydrogen bond. So let's do water. Oops. A little crooked. Let's fix that. All right. Yes, H bond because H directly bonded to oxygen, right? So they can all be within the same molecule, but that doesn't make it a hydrogen bond. They have to be directly connected or directly covalently bonded to either hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. Those are the only three that can do that. And it's almost exactly like a polar molecule. It is a polar molecule. It's just the strongest form of a polar molecule, right? So, um, yeah, it's just the strongest form. So it is a polar molecule, but it's the strongest form of those polar molecules, like the strongest arrangement, I guess, of polarity, right? All right, this is the more confusing one. This is called dispersion forces. Sometimes those are called London forces. I think it's because of a guy named London way back when, right? But we don't need to know that. Okay, let's look at, again, revisiting topic 4, hydrogen and hydrogen. There's no hydrogen that's stronger than the other. So the electrons kind of hover in the middle. So this is non-polar. Let's expand on that. Usually, right? Usually non-polar. Uh, I'm saving this for later. Can happen in all molecules. I'm going to revisit that once we get to that part. All right. So what does that mean? Usually non-polar. Well, usually they're not. Usually those electrons are sort of hovering between those two hydrogen atoms. But electrons are always moving. So electrons always move. So let's take a look at what's happening. So we have H2. I'm going to try and attempt to draw these. All right. A lot of times you have hydrogens just sitting in the middle there. Or sorry, electrons sitting in the middle of those hydrogens because they like to be shared by both, right? But sometimes, again, the electrons are always mobile. So sometimes they look like that. Sometimes, right, they're going to be, so again, this is H2. Maybe they'll be like this. Or they'll be like, I don't know, they're going to keep moving. So they're going to be wherever. Sometimes they're kind of in the middle, or there's going to be moving around, moving around. But every now and then, you'll get this instantaneous moment where both those electrons are on the same side of the molecule. Now, what happens when those electrons are on the same side? Well, there's more negative charge on that side. So there's going to be a temporary instantaneous moment where that side is partially negative. And that means if that side's partially negative, that means this side is partially positive. Well, that can cause other molecules to kind of mimic that, right? If this side is positive, it's going to attract these negative electrons. So they're going to pull the electrons to one side. And that means if we pull them to one side, this other side is going to be positive. So they can chain further and further along so that you have a whole bunch of these molecules as these temporary instantaneous dipoles, and they are temporarily polar, where they are usually nonpolar. So nonpolar molecules, right, can turn polar just temporarily, right? So let's look at nitrogen. Nitrogen, it looks like this, triple bonded, sorry, to that. And so they're both nitrogens. I'm not going to draw all the electrons for nitrogens. We're just going to draw a pair. But nitrogen, sometimes this is non-polar. So what we learned before is, hey, this shouldn't have any intermolecular forces, right? But since every now and then those nitrogens can have the electrons on one side, this is again temporary dipole. And we know that because nitrogen is usually gas, but I know you've heard of liquid nitrogen. So let me start using these things called phases. So N2 is usually a gas, but there is liquid nitrogen, right? If there's liquid nitrogen, we know that there are intermolecular forces occurring because you can't have a liquid without intermolecular forces, right? So needs intermolecular forces. All right, let's do another example. CO2, non-polar. All right, but, have you heard of dry ice? Have you seen dry ice? Right? This is, let's see here. Usually gas, but we do have solid. That's dry ice. So that means if we have a solid of something, it means those things can have intermolecular forces because those molecules are being held together by something, right? Because it's being held together by something, we know there are intermolecular forces there. And the ones specifically for usually nonpolar molecules are going to be dispersion forces because of these temporary dipoles. Again, they're very unstable, so it just takes very little energy to break those apart. That's why when you put CO2 or if you drop liquid nitrogen on the ground, it usually just boils into gas right away. If you put CO2, dry ice on anywhere, you see it just turn into gas because those intermolecular forces are coming apart very, very quickly, right? All right, let's take a look. So intermolecular forces govern those physical states. Again, there's kind of little or no intermolecular forces here, little or none. And this is lots of intermolecular forces, and this is, some intermolecular forces. So the more intermolecular forces you have, the more chances you're going to be a solid, right? A little less, you're going to be liquid. A little to no intermolecular forces, you'll probably be a gas. And we can use temperature or energy to break intermolecular forces. That's why when you put a pot of water on the stove, let's say you put a pot of ice in the stove, turn the temperature up, turn the fire on, you're going to start breaking those intermolecular forces so it goes from a solid to a liquid. If you keep heating that liquid, it's going to break more intermolecular forces and turn to vapor, steam, right? Vapor water, right? Gaseous water. So yeah, intermolecular forces govern a lot of these physical states. Stronger intermolecular forces mean higher boiling points, right? The act of boiling or vaporization, right? Let's say we have a cup of water or a pot of water, right? We have these waters all bonded together, right? Intermolecular forces are keeping those water molecules together, right? They're keeping their water molecules together. What happens is if you have weak, let's put this here, if IMF is weak, bonds, sorry, If IMF are weak, so intermolecular forces. So IMF, right? Intermolecular forces. IMFs break easier. So let's say we had a pot of something like H2S. It looks very similar to H2O. Let me clean that up a bit. That's bonded to HS, right? Okay, weaker. So this is weaker. So what's going to happen? This breaks easier. This is actually stronger. So IMF is strong. More, it takes more energy to break, right? So let's reword this. Requires more energy to break. All right, let's take a look. Water, boom, takes a lot less energy to break. And this is higher because H bonds. All right, this is dipole-dipole only. Right? Since dipole-dipoles are weaker, it takes less energy to break those bonds. Same with HF, H bond. So hydrogen bonds are harder to break because they're stronger. HCl has dipole-dipole, but not hydrogen bonds. Same with NH3, H bonds. The H3, polar, or dipole-dipole only. Or dipole-dipole. They all have, sorry, I forgot to mention that, but they all have all molecules have dispersion forces. Only some are polar and only some have hydrogen bonds, right? So again, dispersion forces can happen in all molecules, non-polar and polar, but hydrogen bonds and dipole-dipoles can only occur in some polar molecules, right? So again, stronger intermolecular forces mean higher boiling points because those bonds are holding those molecules together. And if they're strong here, it's harder to break and turn into gas, right? All right. Another thing that has to do with intermolecular forces is viscosity, is a resistance to flow, right? Let's take water and honey. What is more? Let's get a little better study here. So water and honey. Water or honey? Well, which flows less? If you have room temperature water, room temperature honey, right? Water flows more. Honey flows less. So this is higher viscosity. Viscosity. I'll rewrite that a little bit just to clean it up. Viscosity. Water has lower viscosity, right? So what has stronger intermolecular forces? Higher IMF. This is lower IMF. Again, viscosity is a liquid of a liquid as a measure of its resistance to flow, right? Let's do another one just really quickly. Let's say like water. and Vaseline. Vaseline, right? We'll say flow. This is more. Vaseline flows less. Let's say viscosity. And what was the other one? IMF, intermolecular forces, right? Viscosity is lower, Vaseline is higher because it's resisting flow. If you put a tablespoon of water on the table, it immediately goes into a small puddle and flattens out. Vaseline, you put a tablespoon on that on a table, it just sits there like a big old goop, right? That goop is resisting flow because it's being held together by those intermolecular forces. So this is weaker and this is stronger. All right, so stronger intermolecular forces mean higher viscosity. All right, another thing that this does is surface tension. What surface tension does is it keeps water molecules together, right? And what it does, um, it creates this kind of network of hydrogen bonds because it wants to have the least amount of surface, right? Now, let's say you have a water molecule like this, right? You have some surface here, so a water droplet, right? Or you can lay that water out in a flat line and you have a lot more surface area, right? So more surface, less surface, right? This is surface tension. The water's doing whatever it can to limit the amount of surface. So what it does, it bunches up really tight, right? This keeps it from having a lot of surface area, right? It wants to be, and I say want, water doesn't really want anything, but let's give it some personality. Let's say it always wants less surface area, so it tightens up and balls up because it's trying to achieve the smallest surface area as possible. All right. Meniscus. We talked about this in topic 6 about measurements. We did this in lab. So whatever is happening here, the liquid is either attracted or repelled by the tube. Here, they believe this is mercury. So this is mercury. This is water. So this is, sorry, polar. This is non-polar. What's happening here on the water side is you have the water in the tube. Well, this glass is polar. So what happens is those water molecules, since it likes that polar stuff, it tries to climb up the sides because it likes water is attracted to the polar glass. So what happens is that water is trying to climb up. And so that's why you get that little meniscus. I'm drawing it very exaggeratedly, right? Because water's trying to climb up the sides, but gravity's pulling it down. So you get that meniscus in that shape, right? That shape that looks like that because the water is trying to get on that, right? Let's do the mercury now. Mercury is on this side, on the left side. Mercury is non-polar. Let's do green. So mercury, right? What's happening here is Mercury is like, you know what? I want to stay away from that glass. So Mercury repelled by, or not repelled necessarily, but doesn't want to be next to that glass by polar glass, right? Because this is non-polar. So what happens is it just tries to get away. It's like, you know what? This is like trying to get away from the glass, or it's not compatible with the glass, however you want to say it, but it's trying to move away. So you get that other shape, right? So intermolecular forces are responsible for the meniscus, right? So again, intermolecular forces are a lot to do with kind of drug interactions, things like soap and water, how soap works, all sorts of different things in your everyday lives. All right. Last thing we do is what's something called capillary action. This is very similar to the meniscus. What happens is you have this, again, water is polar, mercury is non-polar. If you have something called, I think this is borosilicate glass or silicate-based glass, what happens, you have attractive forces. And so that water keeps climbing up the tube, but gravity pulls it down. That's why it doesn't go out the top, right? The water keeps climbing that tube and gravity pulls it down. Water climbs the tube, gravity pulls it down. That's why it doesn't go to the top, but the attractive forces. So the IMF, intermolecular forces, is causing the water to climb the glass. Now, if you have a non-polar substance like mercury, capillary tubes are going to be polar. The water's polar, so they're attracted to each other. Capillary tubes are polar, mercury is non-polar, so it tries to get away from the glass to get away from the glass. You don't have to know about this. This is, I think, the forces that take the measurements, and we can measure how far the capillary tube will go up depending on the substance, right? Again, so again, intermolecular forces have to do with the capillary action. So if you have a polar capillary tube and a polar solution, it's going to climb because it likes that glass. Gravity is going to pull it down a little bit. If you have a polar capillary tube and a non-polar substance, let's say mercury, something like oil, what's it's going to do, it's going to try to not climb the glass, trying to get away from the glass as much as possible, so you have a very low level, and anything that is a polar non-polar interaction. All right, that's it. I will catch you next time on the next episode, and thank you very much. Let's see here. How do we get out of here? Let's stop share. All right, I'll catch y'all later. Thank you very much.